Before we go and do new stuff, let's briefly review the count-min sketch, just because we're going to look at some streaming algorithms for this stuff. And this is actually fairly new content, as in you won't find it published anywhere else yet, what I'm going to show you in the end. So this is basically leading to a couple of fun open research questions. Okay, so the count-min sketch, the basic data structure is really simple, and it's a good idea to listen to it because one of the assignments is going to be about the count-min sketch. So we have some item, and what we do is we compute the hash for each of those rows in our data structure, which is a matrix. We compute the hash of this item, and then we increment the corresponding counters by 1. Right? And okay, so therefore, each row is going to contain the sum over how many items I've seen so far. Now, in order to perform a query, I'm going to take the minimum over all those counters, over, let's say, all those red guys. Now, why is this a good idea? Well, since I have all increments, the only thing that could have happened is that some other insert would have incremented any of those counters. So therefore, I know the value in these counters is going to be an upper bound on the true count. That wouldn't be the case if I also had negative inserts. But if I am guaranteed to only have positive or negative numbers in here, basically real inserts, then this must hold. Since all of those are upper bounds, I can take the minimum of those guys, and it's still an upper bound. And the cool thing is, this is a linear statistic of the data, and therefore I can actually take unions between two data sets by just adding those sketches, and I can aggregate over time, I can reduce resolution and so on. And as a matter of fact, we're going to use all of those tricks later on. So again, here are the guarantees. So the lower bound is trivial. The upper bound is a little bit less immediate. And so I'm just going to walk you through that proof again to make sure that everybody's cool with the proof itself. But what it really means here is the upper bound is the actual count plus epsilon times the total number of symbols that I've inserted so far. So that's a good relative accuracy bound. Now, the cool thing is that for power law distributions, you can do even better. And the way how you prove that you can do even better is by saying, well, a power law distribution is one where there are a few really heavy hitters and the rest is really small. So you have like basically 1 over n to the alpha, distribution type. And you then essentially need to deal with two cases. One where we have all bins being, messed up by heavy hitters. That's really bad. And the other case where we don't collide with any heavy hitter at all, in which case, essentially we only need to deal with the tail of what's left over if I cut out the head of the heavy hitters, of the power law distribution. And that is a much smaller component. And then by some fairly detailed analysis, you get that rate, which is, well, faster than 1 over epsilon. So this is actually quite nice. So to get the upper bound, essentially, what we first do is we compute the expectation. So this is a general strategy if you want to compute tail bounds. You have a random variable you want to show that it's well controlled. The first thing you want to do is you compute the expected value of that, because you know that your tail is definitely going to be above the expected value somehow. Unless you have a very pathological distribution, that is. So, well, the probability that I increment some given bin, if I have a random insert x, is of course going to be 1 over number of bins. Because that's the probability that this hash function will put it into this bin. So therefore, in expectation over all hash functions, the increment for a given bin is going to be number of items divided by number of bins. That's basically the perturbation that I get to the hash function. Right? Now, therefore, what I want to be able to show is that at least with high probability, this is going to, my error is going to be within that order of magnitude. Now, the next thing that I then do is I look at the random variable, which is number of counts that my count win sketch gets minus the lower bound that I will see, namely the number of items that I would have definitely inserted. This is a non-negative random variable, and so I can just use Gauss-Markov as I would, and I use Gauss-Markov with an upper bound not n over m, but e times n over m. So I'm just moving a factor of e further to the right. Now by Gauss-Markov, that means that the probability that I go further than that is 1 over e. Now 1 over e is not a very tight bound. 1 over e is ridiculously loose in fact. Now in order to make sure that I get a tighter bound, I need to invoke that 1 over e guarantee enough times that the probability that all of my guarantees fail, now multiplies. So therefore I get e to the minus d. That's the probability that all of those bounds would fail. Each of them is weak, but together they are quite strong. And then all I need to do is just solve for delta equals e to the minus d, and I have the theorem. That's the very simple argument. It's an amazingly beautiful and very simple argument. I mean, all of you here in that room, if they think a bit about it, could easily come up with that proof. When I first saw it, I really thought, wow, this is so beautiful, so simple, it's very powerful, and I just wish I had had this idea before. So it's, yeah, and that happens very rarely, that where you see something that's, so clear and simple, and yet gives you a very powerful algorithm. So, now, what you can do is you can use this to find heavy hitters. It may not necessarily be the best algorithm for it, so space saving is going to be better. But suppose I have something like IP numbers. Then, I could just build a tree of all the IP numbers that I see, and then, at the bottom I get those ranges. And now, of course, it's a good idea, because I don't have very many leaves on top, that, maybe for the first 8 to 10 bits of my IP tree, I keep all the counts explicit. So let's say, for instance, I'm AT&T and I want to find out who's using tethering on their phone without being allowed to, right? Then maybe I compute the aggregates over various IP ranges, and then I only need to drill down into those subnets where the aggregate, data transfer in that subnet is so large that, there at least is a chance that they might have a heavy hitter in it. So, well, in computational advertising, it's not exactly, people who tether their phones without paying a lot more money to AT&T. It's more, let's say we get a lot of requests, a lot of clicks from a specific IP number. That's usually a bad sign, because that may very well mean that somebody is trying to perform click fraud on our advertisers. And so you could build a corresponding data sketch and then drill down. And of course you would want to do that as quickly as possible, which is why sketches are useful. Range, sorry, did you have a question?
Yeah, can we just go back to the proof?
The proof?
I still don't understand why it shifts by E.
Okay. Okay, sure. So let's look at that in very simple terms. So suppose I have some random variable x with a property that the expected value of this random variable equals me. Right? So then, Gauss-Markov tells me that the probability that x is greater than epsilon is less equal than mu over epsilon. That's Gauss-Markov. Now, mu in our case is m over n. And epsilon, in this case, what they picked is e times m over n. sorry, this pen today isn't very good. Oh, all the black pens are gone. So if I pick E times M over N and plug it in here, then this gives me 1 over E. That's exactly what we have here. Sorry, it's N over M. It's on the slides, but I guess you can just swap it in your mind. So now, if I have one of those bounds, and it can fail with probability 1 over E, and I just so happen to have D of them, the probability that all of them fail, since they all can fail independently, since I've constructed those sketches independently from each other by using D different hash functions, is now that failure probability raised to the power D, which is just E to the minus D. That's how the proof works. Yes?
Is Cx the minimum over all your W, I, H, and so on?
Yes. Correct. And so this is basically, so this would have been written out, the probability that the first guy is less than this, and times the probability that the second guy is less than this. And since each of those probabilities can be bounded by 1 over E, the product, since they're all independent, is bounded by E to the minus D. Yes?
Should you have an absolute value on the term? Because from Gaussian Markov inequality, you should have a positive random variable, right? So else you should have a absolute value.
Well, this is a positive random variable. So the thing is, this is the actual counts.
Yes.
This is what we have in our bins. Now, the only thing that could happen to me is that I get some collisions from other observations. So this number is always going to be greater or equal than these counts. So therefore, Gauss Markov applies. It's a non-negative random variable. Okay. Any other questions? Okay, cool. Then we've already found the heavy hitters. Let's do our range query again. So suppose I want to know whether in a certain subnet all machines, what the traffic is there. Now, of course, you could do that explicitly by just checking for each machine, and I could invoke the count min sketch. But that can be fairly expensive, because if I have 2 to the k machines in my subnet, then basically the accuracy is going to be relative. It's going to be a relative accuracy. Now, can I actually improve my accuracy further? Well, the trick is to store the guys on the top of that subnet explicitly. Basically, I don't sketch for maybe 1,000, maybe 10,000 numbers, and I only sketch down on the leaves. Now, what that allows me to do is, if I know this number exactly, then I only need to get a sketch to estimate this part, and well, this maybe is also explicit, but otherwise I would have probably needed a sketch for this guy here, right? So what it means is, I really only pay the price in terms of inaccuracy at the fringes of my interval. And that makes things a lot more accurate than performing the query explicitly. Furthermore, it's also ridiculously much faster, because you don't need to ask for each node down here what the counts are. So basically the accuracy is improved logarithmically, because I only have log side of the interval many boundaries as I walk up the tree. So that can make, again, a big difference. Any other questions on that? Yes?
So it's not clear in my head, where are you placing the sketch? Are you saying that you
So I'm basically using 2 different data structures. So I have a sketch for each of those guys on the leaves here. And so if I want to ask, how many items arrived here, my sketch will tell me. And maybe also for those guys still. But then maybe up here I only have 3 items. I mean, the real tree would be a lot bigger, but that would be very nice to render on the slide. But basically, you could maybe for the first, 2 to the n guys, so maybe the first 1,024 guys, you can just store the counts explicitly. And only everything below is in the sketch. So that allows me to compute these numbers more accurately.
What's the difference between a count and a sketch in this example?
So the counts, okay, so maybe I'm playing a little bit loose and fast with terminology. The sketch is basically what my randomized data structure contains. The actual counts would be, in this case, if I have just a count variable and I increment it whenever I see an item. So for instance, I could have an explicit counter for the number of people who sit on each row, right? I could have another counter for the number of people who sit in the first and the second half of the row. But then if I go down to a much more fine resolution, then finding out how many people sit on each row, maybe on the left half, on the right half of those rows, I might have a sketch. Okay. I think. Well, sorry.
I was going to ask the same thing.
Okay, good.
Yeah, is there a good rule of thumb for knowing when to use a straight histogram or when to use a sketch?
Okay, that's a good question. So, is there a good rule of thumb what to do? Well, first of all, you are going to have a certain computational budget. As in, you need to handle a request in a certain number of maybe microseconds. And that's what some product engineer will tell you. Secondly, you're going to have a certain upper bound on the amount of main memory that you can play with. And of course, if you can store things explicitly, it's always better because you're not making any error. And so you would essentially try to allocate as much as you can in terms of the explicit counts while making sure that the error on the leaves isn't too high. And you'd have to solve a small optimization problem to find out exactly where to put that cutoff. But that would be probably trying out 5, 6 different numbers because you're going to make a cut at the size that grows exponentially in the depth of where you cut in the tree. At least if I have on average constant branching factors, so the number of nodes here as you go down will increase exponentially. So therefore, you'd try out maybe 4 or 5 different numbers. Maybe you would even write your code in such a way that you can just instantiate one of the other and just benchmark it. But that's a very good question. Okay. Now let's move on to the tail guarantees. By the way, I really like it that you guys are asking me questions now. This is good. Thanks. Because this really helps me, also calibrate what is obvious and what isn't. So here are those, Zipfian distributions. We basically have an exponential decay with some exponent z, and some corresponding offset to make sure we don't divide by 0 and just shift it, and this makes sure it all integrates out to 1. Okay. Don't worry about the explicit constants here, they don't really matter so much. So now what you can do is you can basically upper and lower bound the size of the tail, and well, essentially, you solve an integral. That's pretty much what you do. And you can see that basically you subtract 1 from the exponent, and so basically you have k to the 1 minus z being the scaling coefficient for the size of the tail. I mean, that's the interesting part in it. So if I look at the tail of this power law distribution and I start from position k up to the rest, the total number of items that I'm going to see there can be actually very, very small. This, by the way, is a useful way of speeding up and deciding how to cache hard disk requests. And so basically, if you think about it, hard disks may only give you like 100 requests per second. But if I have a distribution that, in terms of its diversity, follows this power law, then it may very well be possible to, to put all those requests onto disk and keep the rest in main memory. So this is something that you may or may not want to do on the back of the envelope at some point at home. But it basically tells you that actually main memory, or maybe an SSD and a hard disk in combination, can give you very high throughput, much higher than what you would expect from a hard disk. Okay, now if we have this, then that basically means only a very small number of really heavy items can exist. We've bounded that sum fairly nicely. After all, this is really what we need in our count min sketch. Remember, we had the number of items over a number of bins, and now this is going to replace the number of items part. And then we basically, bound the heavy hitter separately, and we say, okay, well, if it's a heavy hitter, what's the error going to be? And that's small. If it's not a heavy hitter, then what are the chances that a heavy hitter will collide with us? Well, that is also small because the heavy hitters are few. And then if I don't get a collision with a heavy hitter, I essentially appeal to the count min sketch argument again. And you can actually look that up in a fair amount of detail in Graham Cormor's and Muthu Krishna's paper. So what they specifically do, and I'm not sure we should go through this in great detail, but basically they say, well, the hit is 1/3 of all the bins. So then the probability that we don't hit the head is 2/3. Makes sense. And then I need to make sure that, essentially I apply my standard argument for the case that we don't hit, and then for heavy I do a separate reasoning pattern. Okay, basically this is what you get. So you get, rather than 1 over epsilon dependent, you get 1 over epsilon to the minus minimum of 1 and 1 over z. So that's the amount of space. So the larger this z is, the smaller this number becomes. And so it basically means that I can get much higher accuracy with sublinear amount of storage, which is really cool. And that's exactly what you would expect from a parallel distribution, because it almost degenerates into a data structure where I have one set of storage for the heavy hitters and then the count min sketch for the rest. So if you look at the analysis, that's pretty much how it works. Okay. Now, there are a couple of ways how you can actually tighten up heavy hitters. So there's a very nice paper by Montanari and co-workers called Counter Braids. It's so nice that it even got the best paper prize. The only unfortunate thing is, good luck trying to find a complete proof. So it's in some forthcoming paper of Andrea Montanari, or some book possibly. I have not been able to get my hands on the full proof, so we are not going to go through the proof. Fortunately, the algorithm is insanely simple. The proof isn't. It's quite the opposite of that. So think of our count min sketch. What really happened is that we had all those inserts, and we're going to get some collisions on that bin. And I'm going to put myself into the not quite unrealistic, but not always applicable scenario where I actually know the identities of the items that I would have inserted. So at some point, I have a list of all the things that I could insert. For instance, with IP numbers, that's very straightforward, and that's actually the applications scenario that they looked at. They basically looked at switches which have very little memory, but on an IP4 network, you have only 2 to the 32 different IP numbers, so I know what my range of inserts is. Now, what we use in the count min sketch is that a priori, we have this lower bound on account of being 0. We didn't have a tighter lower bound, but so therefore, the only thing that I could do is I could really take the minimum over all those bins and say, well, this is going to be an upper bound on the number of counts. Now suppose that this minimum kicks in here, but I'm telling you that actually rather than 0 instances of y, we would have seen 10 instances of y or more. I give you a tighter lower bound on these guys. Then you can use that to work out a tighter bound on x, right? Because if I know these two y's collide, and I've seen at least 10 of them, then I can take this number and subtract 10 from it, And it's still an upper bound on the x guys, because it still could have collided with the z's or whatever. Yes?
Should the IX should be I at IX because it's a minimum of counting, not about hash function, right? You see,
yes, absolutely. It's m of yes, absolutely.
Yes.
Thanks. Was that wrong on the previous slide too, or did I cut and paste wrongly? Okay. Thanks. Thanks for paying attention. Good. So yes. So basically, what happens is, if I knew a better lower bound than 0 for all of these guys, I could come up with a tighter upper bound on these. Right. Furthermore, so what we're actually going to do is we get an upper bound on those x's. Right. Now if I have an upper bound on all guys, and I look at this bin, let's say I know that at most I had 20 collisions from x and y, and I record 50 here. Then, and I know z is also in the mix, then z must be lower bounded by 10. Because in order to arrive at 50, and if these two guys are upper bounded by 20, z must be at least 10. So I can basically use the fact that this bin value here is the sum over the counts of these three to work out upper and lower respective bounds for one variable conditioned on everything else. So in other words, I get upper bounds for one by taking the lower bounds for everything else, and I can get lower bounds for one by taking the upper bounds for everything else. So initially I start off with the lower bound being 0 for everybody. Then I just run count min, and I get upper bounds for everybody. I then go and use the upper bounds as lower bounds for everybody again. And I keep on iterating this. So it's almost like constraint propagation. So I basically have a lower set of constraints which give me a tighter upper one, and the tighter upper set of constraints is hopefully going to give me a tighter lower set of constraints. And the ingenious part of their analysis is that they can actually prove that under certain not too unrealistic conditions, this algorithm converges to the correct count, which is quite awesome. So even though you have this approximate data structure, by just propagating upper and lower constraints for long enough, they can show that with high probability this will converge to the correct numbers. Okay.
Seems you're running a circle here. You need
Yes.
x prime to bound x.
Correct.
And to bound x prime, you need a.
Absolutely. And so what you do is at stage 1, you have lower bounds for everybody.
Okay.
Then you use those lower bounds for everybody to get upper bounds for everybody.
Alright.
By using the lower bounds of everyone but that variable that you have. And you do that for all the variables. Then, with those new upper bounds, you get tighter lower bounds for everybody. And this tightens the gap successively.
Okay. So the theorem says the gap goes 0.
Yeah. And essentially, the argument that they make is if you had a tree through which you propagate this, then you can show with only like about 1 page of math that this is reasonable. And then they say, by the way, we don't have a tree but the directed graph. And in this case, it's essentially tree-like locally, and it looks sufficiently tree-like locally that our proof still goes through. And it's a not obvious proof.
It looks really similar to EM.
Yes, it's sort of similar to EM, or also sort of similar to message passing in graphical models. Yes. Yes.
So how do you get the initial lower bound?
Well, initially you know that that all your counts are non-negative. So for instance, if you're logging traffic, you know you can't have negative traffic. That's your lower bound. So the lower bound is 0 throughout.
Then can we just do first couple iteration?
Well, I mean, you know, you have to so if effectively count min implicitly uses this lower bound, right? So if I didn't know that my lower bound is 0, I mean, maybe I can use some other lower bound, right? And I don't know whether the analysis would still go through. Might be actually a fun question to think about. It should, because I mean everything is just linear and additive, so it may very well work. But the first lower bound you get for free. Everything else you need to iterate. And therein also lies one of the disadvantages of this counter braid algorithm, that you basically need to really look at all the instances that your sketch could have seen. So you pay big time in terms of reconstruction. Because for count min, your lookup is essentially order 1. You just look up, you know, log delta many counters, and you have your upper bound. For this, you need to really, you know, cycle through the entire data structure until the algorithm has converged, and then sure you have all the counts at once, but it's not so easy to get just a single count at any given time. So that's what makes the algorithm a little bit less attractive in practice. Okay?
To clarify, do you do this iteration, do you need to be able to enumerate the keys that have?
Correct. And this is the killer in many cases. So for IP ranges, it's trivial because you know that you have, you know, 2 to the 32 different keys. If I wanted to do that with text, it could be a real problem. Or if I want to do that with user cookies, you can pretty much forget about it. But for certain cases, this works. Now, here's another really cute thing that they do.
Can I ask a question?
Sure.
Very stupid. So, how could you say that the lower bound and the upper bound is kind of together decreasing? Because
well,
the lower bound seems is more and more decreased when you kind of you see it.
Okay, so first of all, you know that your bounds always have to get tighter, because if you had a bound before and your new bound isn't tighter, you just keep the old bound.
Okay.
Right. So because the previous one was a bound and this is a bound, so you know the maximum of the 2 lower bounds is still going to be a bound. So therefore, things never get loose. To show that it converges, that's the non-trivial part, and that would be, yeah, probably more than 3 hours of explanation.
Okay. So I say basically, so when you get a lower up bound, using up bound to plug in the lower bound case to get a higher, lower bound, then just like this. Okay, thanks.
Yes. So you can actually use a similar argument to infer when users might have signed up and started following each other on Twitter. So basically what you exploit there, and there was an interesting paper last year, you use the fact that the sign-on, that basically the follower lists and the followee lists are chronologically ordered. Twitter doesn't reveal when you followed somebody else, but it's ordered in a monotonically increasing order. And then you can essentially use the same argument to tighten up your estimates. They didn't do that in the paper, they basically did the first count min sketch type argument, but you could tighten this up. Now, the really cool part is that you can actually iterate this data structure. So what happens is the following. If you allocate enough space in your count min sketch, you're going to end up with a lot of zeros. And you may not necessarily want that. So what you can do instead is, you can actually, you do something that's very counterintuitive. You basically take counters which have only a small bit resolution, let's say for instance 8-bit. Of course those counters are going to overflow. But then what you do is you pipe those overflows into a subsequent count min data structure. And then you pipe those overflows into the next one. And then you run counter braids on top. You could reconstruct things. You use this to know exactly which overflows and how many you had at the next level. So you basically get that additional bit resolution here. You then run counter braids on these guys, and you work your way down. So this gives you a highly non-trivial data structure, which is very space efficient, but computationally quite expensive. Given that it's 5 right now, let's have a short break, and then we reconvene in 5 minutes.